Hello everybody, resuming back, we have been discussing about diffraction, that is Fraunhofer diffraction at a single slit. We have already understood the difference between Fresnel diffraction and Fraunhofer diffraction, and I have discussed about the Fraunhofer diffraction at a single slit a little bit in our last class. So we are resuming again our class on Fraunhofer diffraction at a single slit. Here we consider a slit AB. AB is a slit and it is rectangular in shape and it is having a width small letter a, and the width of the length is large compared to the width a, small letter a. And here we assume that the parallel wavefront is approaching the slit AB, and this wavefront is made parallel by keeping a lens in between the source of light and the aperture or the slit. And we all know we are discussing Fraunhofer diffraction. To make the rays coming from infinity, we have to keep a lens in between the aperture or slit and the source of light. And we assume that the rays which are coming directly into the slit or passing through the center of the slit will move undeviated and will choose a path so that it reaches the point O on the screen. Right. Again, we know that in Fraunhofer diffraction pattern, one more lens is kept between the slit and the screen. Right. So what happens is that all the rays which are coming parallel to this undeviated ray will reach the point O, such that all the rays reaching the point O will be having the same phase, or there is a constant phase difference, or they are having the same phase. And what happens is that there is no path difference between these rays and there occurs a constructive interference at the point O. We are discussing about the secondary waves which are emanating from the slit A, B, and what type of superposition is occurring for the secondary waves on reaching the screen, which is kept in front of the lens. And at the point A, what happens is that all the rays proceeding in the same direction as that of the incident ray get focused at the point O on the screen. And what happens is that we'll have a primary maximum there, or a central maximum there, and you can see the diffraction pattern, and this is the central maximum, and all the waves coming at this point will be having same phase. Right. And what happens next is that we assume the points on either side of the central maximum. As an example, we assume the point P, such that the rays get scattered or deviated from the corner of the obstacle or at the slit A, such that it follows a path A P, and at the end B it follows the path BP. Right. And what happens is that it gets deviated at an angle theta from the ray of the incident, or the direction of the incident light. And now what happens is that normally from the figure itself it is understood that the path length is different for AP and BP. So what makes the difference in the path length is this small region, and I'll just name this as BK, since a perpendicular is drawn from A to reach the line AP such that it meet at the point K, and it is not mentioned in the figure, so just assume this point as K such that BK is equal to delta will be our path difference. BK is equal to delta will be our path difference. And what happens is that here the light gets scattered through an angle theta, and we are drawing a perpendicular to the line AP. This is the line drawn perpendicular to AP, and to the line AO, AB is perpendicular. And you all know that from the basic geometry, if two lines are making an angle theta such that we are drawing perpendiculars to these two lines, it also makes an angle theta. And we got the angle theta here. It is not also shown in this diagram. And what happens here is that we can assume a triangle ABK such that this is the triangle, this A, B and AK, BK are the sides. And from this triangle, this angle is theta, such that we'll get sine theta is equal to opposite by hypotenuse. Opposite is our BK, and BK is actually our delta, which is the path difference. And the hypotenuse is AB, and it is equivalent to A, which is the width of the slit. And what I'll be getting here is that sine theta is equal to BK by AB and BK by A. So we'll get BK, which is the path difference, is equal to A sine theta. And corresponding to this path difference, we'll get a phase difference. That is, for lambda path difference, we have a phase difference of 2 pi. So for for unit phase difference, you will have 2 pi by lambda into 2 pi by lambda path difference, and for capital delta path difference you'll have delta is equal to 2 pi by lambda into delta phase difference, which is equal to 2 pi by lambda into A sine theta. You'll have to keep these equations in mind. This is very important, this equation 1 and equation 2. So what we have got here is the path difference between the light rays coming from the point A and the point B reaching at the point P is A sine theta, and corresponding phase difference is 2 pi by lambda into A sine theta. Okay, so the next question is, what type of superposition takes place for the secondary wavelets coming at the point P or reaching at the point P? Reaching at the point P. Okay. And if we assume that the secondary wavelets starting from A and reaching P, similarly the secondary wavelets starting from B and reaching P is having a path difference delta, which is equivalent to integral multiple of wavelength lambda, we'll get a minimum at the point P. So it will be a point minimum intensity at the point P if the path difference is an integral multiple of lambda. So normally question arises. We have already studied that in the interference pattern, you have studied that if it is an integral multiple of lambda, what you'll be getting constructive interference. If it is an odd integral, half integral multiple of lambda, you'll be getting a destructive interference. And what we have obtained here is just the reverse of that. So why is that so? Because we assume that from A to B, we are moving from A to B, the secondary wavelets will have a path difference which is simply equal to lambda. And we assume a point O at the center of the slit, that is from A to B, at the center, this point we assume this point as, here it is mentioned as O, just I'll take it as O, such that the wavelets coming from A and O will have a, comparing the wavelets coming from A and O, the path difference will be lambda by 2. Again O and B will be lambda by 2, and hence it is in effect there is a path difference. This whole AO produces net path difference lambda by 2, and the same is reciprocated, or the same is observed here also in net effect, producing a minimum intensity due to destructive interference or destructive superposition, producing a minimum intensity at the point P. Okay, so the condition for minimum for in the case of single slit Fraunhofer diffraction pattern is path difference A sine theta is equal to n lambda, then we'll get a minimum. And as usual, if theta is very small, I can approximate sine theta is equal to theta. Then what I'll be getting is theta is equal to n lambda by A. Similarly, if the path difference is an odd integral multiple of lambda by 2, what happens? It will normally be we have a central maxima already at the center, so it will be, I'm going to name it as a secondary maxima. Central maxima is already there, so our name is the maxima itself, but it is a secondary maxima, and it is 2n plus 1 lambda by 2. Normally sin theta, then theta becomes as in this case 2n plus 1 lambda by 2a. And if you are giving n is equal to 1, 2, 3, you will get first, second, third secondary maxima, and the intensity of this maxima goes on decreasing as the order n goes on increasing. So hope this is clear. We have found out the path difference for the secondary wavelets. The condition for minima is a sin theta is equal to, the condition for minima is this, and the condition for maxima is this. Fine. So we have found out the path difference, the expression for path difference, condition for minima and maxima. So next is, what is the expression for the intensity? So according to the Huygens wave theory, we assume that the plane wavefront reaching the slit AB spread out secondary wavelengths which interferes to give the diffraction pattern on the screen. And let us assume that there is n number of secondary wavelets of the wavelength that is incidenting on the slit AB. So the resultant amplitude due to all equal parts of this slit AB at the point P can be determined by the method of vector addition of amplitude. And this method is also known as polygon method. And for this we are going to construct a polygon of vector having amplitude A0, and it represents what? The amplitude of each of the wavelength emanated from the slit AB. And the direction of this vector is represented by phase of each wavelets. And you can assume, you can see here that the phase difference between the wavelets starting from the point A and moving to the point B, such that if you're drawing the tangents, you'll get the phase difference delta. Delta is the net phase difference of the wavelengths as we are moving from the point A to the point B. That is the phase difference of the wavelets emanating from point A and B, be delta. And we assume that all this constitutes an arc, and this arc is a part of a circle, and this circle is having a radius r. Normally if this angle is delta, what happens here is that this angle also will be delta by basic max. And if you are drawing a bisector CN to this triangle, what happens is that this angle becomes lambda by 2. It is a perpendicular bisector, and this side is same. It is actually similar triangles, you know, these two sides are same, and this side is equal to what? The radius of this circle. And what happens? This angle becomes lambda by 2, this angle becomes lambda by 2, and the resultant amplitude of the waves starting from A to B is actually R. And I am drawing a perpendicular bisector CN, so the resultant amplitude becomes R by 2 here and R by 2 here. I'm just we are using a polygon method of vectorial addition. So what happens here? I'm having an angle delta by 2 here, and we are having two similar triangles ACN and BCN. Assuming the triangle ACN, you will have sine delta by 2 is what? Sine delta by 2, that is angle. Or simply I can assume the angle. Angle is equal to what? Arc by, before that I can assume here angle is equal to, before that I assume the net arc here, and this is what? Angle. Angle total delta is equal to what? Arc. This is the arc and R is the radius. And what happens here is that this arc is actually made up of n number of secondary wavelets, each of having amplitude A0. So the net becomes n into A0. That is n into A0 by R. And you can find out the radius of that circle is equal to n A0 by delta. Now we have drawn a perpendicular CN, I have mentioned before, and now we are going to assume two similar triangles here. First I assume the triangle ACN and then BCN, and what you will get? Sine delta by 2 is what? R by 2 divided by R. That is, sine delta by 2 is R by 2 divided by AC. Sine delta by 2 is R by 2 divided by BC. And you can find out R. You just think of it. Our intention is to find the intensity. For that, we need amplitude. And now we are going to get the amplitude. I have told R is the amplitude. So R by 2 is equal to A sine delta by 2. And we have AC is equal to BC is equal to R. From that I can get R is equal to 2R sine delta by 2. And putting the value of small r, that is small r, NA0 by delta, substituting it here NA0 by delta, you will get what? NA0 by, I'll take 2 to the denominator, delta by 2 sine delta by 2. Okay, so what is this? I have mentioned earlier that delta is the phase difference between the secondary wavelets starting from A and B. So corresponding to this phase difference delta, there will be a path difference. Delta is equal to 2 pi by lambda A sine theta. Since here it is delta by 2, what I'll get? I have already told, we have already discussed it here. Delta is equal to 2 pi by lambda A sine theta. Okay, so it is delta by 2 means pi by lambda A sine theta. And I'm going to mention it for the sake of simplicity. Instead of delta by 2, to make the equation easier, what I'm going to substitute it as alpha. This is A, this is alpha. Don't get confused. So what I'll get? I'll get the resultant amplitude R is equal to Na0 sine alpha by alpha, and the square of the amplitude is intensity. So our intensity is I is equal to I0 sine square alpha by alpha square. Right, we got the expression for intensity in the case of Fraunhofer diffraction due to a single slit. Now we'll just check out the intensity distribution. That is what happens, how come the central maxima is going to have a maximum intensity. For the central point O on the screen, you can see the point O on the screen. What happens? Theta is 0. When theta is 0, what happens? Sin theta is 0. Theta is 0. What happens? Sin theta can be approximated. Theta is very small. Sin theta can be approximated as theta. And what happens here is theta is very small in the limit as alpha tends to. When theta is equal to 0, alpha will also be equal to 0. That is, in the limit alpha is equal to 0, sin alpha by alpha is equal to 1. So we will have I is equal to I0. That is the maximum intensity point. At the point O, we'll have, it is point O on the screen will have maximum intensity. And principal minima, what happens in the case of principal minima? I is equal to I0 sine square alpha by alpha square. For getting minima, what happens? Our condition is alpha is equal to n pi. That is sine pi 0. N is equal to 0, sine 0, sine pi, sine 2 pi, sine 3 pi, sine 4 pi. For everything, what happens? Intensity becomes 0. So I'm putting n is equal to 1, 2, 3, 4, 5, etc. But I'll get the minimas here, the position of all the primary minima, first minima, second minima, condition for minima. So the intensity for central maxima, principal minima, and I have already discussed the condition for principal maxima there. And if you we can discuss some of the problems, and while doing the problems things will be more clear to you. So again, you can see the intensity distribution due to a single slit diffraction. Maximum intensity, central maximum, alpha is equal to 0, alpha is equal to n pi, 2 pi, 3 pi, etc. You will get minima. And the condition for secondary maxima is what? Alpha is equal to pi by 2, 3 pi by 2, 5 pi by 2, etc. I have already mentioned there in terms of lambda. Okay. So hope you have understood about the Fraunhofer diffraction pattern due to a single slit. And what we have to do is we can discuss, you just go through this slides, and we can discuss. If there is any doubt, you come to me, we can discuss there. We can discuss some more problems also. And before that, winding up, you can there will be some questions from this part, that is like what will be the width of the central maxima. Okay, just bear with me. We'll discuss this too and wind up in this class. The width of the central maxima can be divided as a separation between, on either side of the central maxima, you'll be having two minimas, right? And this is the point O on the screen. On either side of this central maxima, we'll have a points of minima. And we assume that the distance from the center of the screen to the first minima is x, and it will be towards the top and bottom. And we already know the expression for path difference. It is lambda is equal to a sine theta, which is n lambda. And what happens here is that if you are putting theta is equal to theta 1, which is approximated as sine theta is equal to lambda by a. And if you are assuming this theta is equal to theta by 1, and this theta is very small, what I'll get? We already have expression for sine theta, and we are going to, from this figure, we are going to find tan theta. And in this, we are going to get, we have assumed two distances. Since this is the lens and the screen is kept at the focal plane of the lens, what happens? This distance becomes f, and the distance between the slit and the screen is d. And what you'll get? Tan theta is what? Opposite by adjacent, that is x by d. And since this lens is kept very close to the slit, what happens? D can be approximated as f. So what happens here is that theta is very small, means sine theta 1 is approximated as tan theta 1, which is approximated as theta 1. So on comparing these two equations, what I'll get? Theta 1 is equal to what? Lambda by alpha, which is equal to x by f. From this I can find out x, that is lambda f by a. So what happens? The width of the central maxima is what? 2x, 2 times x, this distance into distance, that is 2 lambda f divided by a. Right. So if we are given the wavelength of the light, focal length of the lens, and width of the slit, you have got an expression to find out the width of the central maxima. And this result is very important, and there will be problems from this session. Hope it is clear. That is Fraunhofer diffraction due to a single slit. And in the next class, we'll discuss about diffraction grating. What is the expression for the path difference, and what is the condition for the intensity distribution or the diffraction pattern, order of the spectrum and all. And then we'll discuss the resolving power of the diffraction pattern and how you're going to find out the wavelength with the help of a diffracting element. With that, we'll finish our portions. That is second sum portions. If there is any doubt, you come to me. So thank you all.